So the last time we went over 7A, we introduced probabilities. I can go from 0 not happening to 1, it's guaranteed to happen. So probability is a decimal between 0 and 1, or a fraction between 0 and 1. It tells you kind of the likelihood that something's going to happen. And we had theoretical probabilities. So we made a bunch of assumptions about things being random or equally probable to happen, like rolling a dice or something. You can figure out the theoretical probability of a die. And then we had relative frequency. So that's like you're looking back on something. So we're either predicting something with theoretical probability, or we're looking back on something with relative frequency and seeing how many times the event happens out of the total number of outcomes. Either way, when you're talking about the probability with relative frequency or theoretical probability, it's kind of solved in the same way. We have like I said, the number of times the event occurs over the total number of outcomes. And any questions over the first chapter stuff? That, and I think we also did probability tables. So I'm hoping you should be able to do that sort of stuff. Okay. Before we're Stephanie. I don't think she logged in yet. Oh, there we are. Okay. So the first chapter is basically we're introducing probabilities. This chapter, we're going to combine probabilities with things like and and or statements. Oh, well, this is slow today. And so the first few questions, they ask us some sort of true or false question. The probability of getting heads and tails when you toss a coin is 0, but the probability of getting heads and tails is 1. Heads or tails. I said that wrong, didn't I? So the probability of heads and tails is 0. Probability of heads or tails is 1. And so what is this saying? If we think about heads and tails, this means we're getting it at the same time. So if you flip a coin and you get a heads and a tails at the same time, let me know how you're doing it, because that's a new one on me. But this is saying it's 0, it's not going to happen. You're never going to get a heads and a tails at the same time, but a heads or a tails. Are you going to get a heads or a tails, one or the other? You're guaranteed to either get a heads or a tails when you flip a coin. And then I always have some smart ass that's always like, what if it lands on the side? Yeah, we're not doing that. When you flip a coin, it's going to land flat, right? Heads or tails. If it flips a coin, they cheated. Tell them, get out of here. Decide whether each of the following statements makes sense or is clearly true, or doesn't make sense is clearly false. Same thing. The probability of drawing an ace or a spade from a deck of cards is the same as drawing the ace of spades. Okay, and so I think you're probably getting this. But an ace or a spade, this is 4 cards, and this is spades are 13 cards. And then I think we maybe have to subtract 1 for what they have in common. But here we're talking about 16 cards, I think, and here we're talking about 1. And so you might figure out drawing a single card from a deck is going to be a lot more hard than drawing this group of cards. Ooh, who said true? Why'd you say true? The probability of drawing an ace or a spade is the same as drawing an ace of spades. That's not true. and probabilities. Okay, so now we're getting into and probabilities, and then I think we do or probabilities, and then we do some mixed practice. So they kind of set you up to hopefully get you to understand the concept, and then they're going to kind of turn you wild, and you're going to have to try to figure it out on your own. So if we getting 5 heads when you toss toss 5 fair coins simultaneously. Are these independent or are these dependent? So when I toss a coin, if I toss a coin over here and I toss a coin over here, is this coin influencing this coin when I flip it? Oh, almost hit the wrong one. And so what do we say? Are we getting this concept? And so if you think about flipping coins, if I flip one coin, it should not influence the outcome of the other coin. And so these are independent events. Flipping coin 1 is different from flipping coin 2. It's not going to influence it. My probability on each coin is still going to be a half. So my probability does not change. Are they going to make us figure it out now? I think we did it once, and now we got to figure it out. Let's see. Well, how much do I want to give y'all? All right, so think about each of the probabilities. We get 5 coins, 1, 2, 3, 4, what, 5? And so I talked a little bit about it, but the probability of my first coin, if I want a heads, the probability of getting a head is a half. And so I want to combine this. And so I guess my question is getting 5 coins going to be like more rare or less rare than getting, yeah, did I say that right? Getting 5 heads, is that going to be more or less rare than getting 1 head? And what do I do to these probabilities to combine them? So this was the and statements. Let's say there's a few ways you can combine numbers, and I kind of hinted at it. Each of these is independent, so if we're thinking heads, tails, I do believe it should be 0.5% all the way, or half, not 0.5%, half probability. And so if we want to combine them, if we want to do things together, what are y'all telling me? 1 out of 32. Oh, 0.3125. So for the most part, I believe I'm putting my probabilities in reduced fractions. So I think you did. Yeah, that's 1/32. So that's right. It's just I didn't put it in that format. But we have the first head, second head, third head, fourth head, fifth head. We have a half probability all the way through here. I know my multiplication sign is a little bit low here. It probably should be a little bit further up, like right here or something, right? We're doing a half times a half times a half times a half times a half. If we look at the numerator, it's nothing but ones. So our numerator should be 1. Our bottom should be 2 to the, what, 5th, I believe? Oh, come on. Next slide, next bullet. And so we're multiplying 2 5 times. For some reason, I had a few students in the last class, they kept multiplying these numbers. They would do 5 times 2 or something like that. I'm like, no, like you're not adding these numbers, you're multiplying them. So please don't do that. It doesn't work too well. Questions about this one, about how to get this? And so these are independent trials. This one's not going to affect this one. It's not going to affect any of those, right? Each of them are its own little thing. And I think the next one, let's see. Any questions on this? if it helps.
No.
Like even if you want to look at two, right? If we flip one head or one coin, there's two outcomes. It's 1 out of 2. If we're thinking about two heads, there are 4 outcomes. So this number on the bottom should like kind of correlate with the number of outcomes you have, right? There'd be 4 outcomes here. There'd be 8 outcomes here. There'd be 16. There'd be 32 different outcomes. And you're only going to get all heads one time. So I did it last time, and we don't want to have to like do this thing every time. But if I wanted to, I could go heads, 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 right? Heads, 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 tails. I could start listing every single stupid outcome. We don't want to have to do this every time. So having some sort of method that's mechanical that gets you there, it really, really helps you not have to do this work, right? But if I wanted to, I could circle the thing that's all heads. It would be 1 out of the 32 different options I could list. I could do all the possible outcomes. Not something I would want to do. List 32 different combinations of letters, H and T's. Not the most fun. Randomly drawing and immediately eating 3 M&Ms in a row from a bag that contains 10 red M&Ms out of 30 total. Okay, so is this independent or dependent? And I will give you a little bit of a hint here. They say something about eating 3 red M&Ms in a row. And if you eat them, guess what? You're not going to return them to the bag. So this is something they will call without replacement. So whether or not you replace something makes a difference. And so they say eating 3 M&Ms in a bag. That's called without replacement. And I'll talk a little bit more on the next slide about maybe how to figure that out. But if you're not replacing them, what's happening each time? When I draw my second M&M, what's it going to be? It's going to change a little bit. So I think, hopefully, I'll answer this correctly. Let's see. Yes. Okay. That's correct. Oh, shoot. What the heck? I hit my bookmark for grad college. Okay, that's not what I was trying to do. I was trying to clear my annotations and go to the next slide. That's what I was doing. Okay, now we want to figure out the probability of drawing this thing. So we have 30 M&Ms. We have 10 that are red. And here's my first M&M. 1 M&M, 2 M&M, 3 M&Ms. Where are we going? 3 of them, that's it. Okay, so my first M&M is the occurrence. So I think I got what, 10 out of 30? I should really do this with some text, right? 10 out of 30, I believe, is my first M&M. So when I draw my first M&M, I'm getting something like 10 out of 30. What am I going to get for my next one? Just delete this stuff. Come on. So if I draw red M&M and I eat it, how many M&Ms do I have? How many red M&Ms do I have left? If I start with 10, I draw one and eat it.
Would it be 9?
Yeah, and then how many total M&Ms do I have left?
29.
29, that's it. We do it about down by 1, right? If I take 1 out and I eat it, I'm going down by 1. I have 1 less red M&M. I have 1 less total M&M. All right, so what was I going to say? 1 M&M, right? 1 M&M, 2 M&Ms. We got to get 3 M&Ms. So if that's how I do my second M&M, what is my third M&M going to look like?
Eight over 28.
Ooh, that's it. And so, like I said, for most of these, I believe I put in reduced fractions. So these are a little bit more involved than the independent events, I believe. There is a certain pattern though to get here, right? We're going down to 1 each time. 8 out of 28 is what you said. If we want this and this and this to happen, where are you at? There's one person. Either that or my computer's lagging. Shouldn't be multiplying those things through. Who's this, Ricardo? Are you getting it?
I'm trying to like get it to. Do I try getting it to the smallest fraction, or do I just put it in like how I got it?
Should get reduced.
Okay, because I'm kind of having a hard time reducing it. That's why.
All right, you got a calculator?
Yeah.
You got the frac button? Has it got it on there?
No, I'm using my phone right now.
You're using what?
My phone.
Okay. It should be on there too.
Really?
Can you expand the keyboard? Oh shoot.
Yeah.
I thought your phone calculator's added on there. Maybe it doesn't. One, 2, 4, 3, 6, 0. Let's see. I don't see it.
Put what it equals. That way.
Yeah, I mean, if you put it in there, I think it's may not count it right if it's not reduced, but I'll tell you. Okay, so what did you say? 720 out of what? 24? What was it? 24, 360? 6 out of 203. Is that right? 6 out of 203. 0.0295566, something like that. 29. Yeah, it should be 296. That's it. So I would put the fraction in there. Before I start rounding stuff to a decimal, I would put fractions just because they're more accurate. And I think it was like what 720 out of 24 360 or something crazy like that. But 10 out of 30. If we pull out the first red, I talked about this already. It should look something like this. And 720 out of 24 360 gives me 6 out of 203. When I reduce it, I think they're both reducible by what, 90 divided by 90. You can always do this trick, right? Take out the zeros, and then they're both divisible by 2. And see if they're divisible by what, 3, I think. Should be in there. Okay, so a little note here. 10/30ths is not reduced. And it might be, I want to say, there might be something nagging at you to like reduce this, right? I would not reduce this, because when we look and we get here and we start doing this one, we have to take one away from here and one away from here. And if we reduce it to a third, it's going to be a lot harder to do that. So I would not reduce these until you're kind of done with this, or at least until you're done with this step. Because if you do, you might run into some troubles trying to do this, trying to do the dependent sort of thing happening here. So this is the dependent pattern. Any questions about this? So if they're independent, they're not affecting each other, we can just keep the same kind of probability. If they are dependent, we have to think about it a little bit more. We have to do that pattern. So determine whether the events described are independent or dependent, selecting an all-male 5-person jury from a pool of 10 men and 10 women. And so when you select these people, you're going to select them kind of one person at a time. Someone in my last class asked me, are we going to do one at a time or all at the same time? If you do all at the same time, I'm not sure how are you going to do that. But, ooh, I just closed out that window and I didn't need it. And if I select people, there are 20 people total. And I select a man, is that going to influence or change the way I select the next person? What are we saying? Dependent? Yes, each one is going to change. And I kind of said it a little bit, but I'll say it a little more. We want to select 5 people. So you know you have to make 5 decisions. So I'd probably, personally, if I was doing it, I'd probably draw the line there. And I know I start out with, I believe, 10 men out of 20 people total. And you told me this was dependent. So how does this look? $21 out of 1292. My response is 21 out of 1292. What'd you tell me? 7? I'm not sure I'm getting 7. Okay. I think you're off by a factor of 3 somehow there. But you want 5 men? There's your 5 guys. How do I get 5 guys? I think you just got to walk up to the counter and order it. But yeah, let's make things more complicated since we're math. 10 out of 20 is my first man. I'm going to take away 1 man. I'm going to have 9 men left out of 19 people total. When I go to select my second man, I'm going to select my third and my fourth and my fifth. It's going to go down 1 each time. So this was the pattern that we talked about, discovered last problem. Here it is again. And when I multiply these numbers on top, 10 times 9 times 8 times 7 times 6, I get 3240. When I do 20 times 19 times 18 times 17 times 16, I get the 1,000 or million. 860,000. I divide each of those by, what is it, 1440, I believe is the number. If I divide the top and bottom by 1440, I should get 21 over 1292. Man, okay. No, you're not going to be able to use your phone on the test, but you're not going to be able to use Wolfram Alpha either. So I guess if you wanted to, I know Wolfram Alpha will reduce fractions for you if you need something to reduce fractions. Okay, and we were doing and probabilities. And so I will say I want a head and a head, and I want another head. I want 5 heads in a row, right? It's like saying I want this head, and I want this head, and I want this head. Here we're doing or probabilities. So when I'm doing and probabilities, I'm not being very specific, or I'm being very specific when I say and. Or probabilities, now we're going to talk about whether these things are overlapping or non-overlapping, these events. So if I'm talking about getting a sum of 2, 3, 4, 5 on rolling 2 dice, we're going to talk about 2 6-sided dice. So last time we did 4-sided die, and we did a table with that. Now we're doing 6-sided die. And if I get a sum of a 2 or a 3, can I get a sum of a 2 and a 3 at the same time? That would be overlapping. Means that they can happen at the same time. Non-overlapping means these are never going to happen at the same time. So this goes back to Venn diagrams even, right?
Wait, I'm still confused. Can you explain it again?
Okay, so we're talking about getting a sum of 2, 3, 4, or 5 when we roll 2 dice. And overlapping means that these can happen at the same time. Non-overlapping means these cannot happen at the same time. So if we roll 2 dice, is it possible that we have both a sum of a 2 and a 3 at the same time?
Both being sums?
Yes. If we roll 2 dice, is it possible that they're going to sum to 2 and they're going to sum to 3 at the same time?
Oh, okay. That makes sense.
Yeah, it should sound kind of silly, hopefully. So can they happen at the same time is what we're talking about. Why is it not ending this? We all answered. Lost my connection. Okay, come on. Quizzes. And it should sound silly because they're not going to happen at the same time, right? If I roll 2 dice, that sum is very distinct. It's not going to be both of those at the same time. Oh, come on. We're done with this question. If we all get this correct, someone saying something else? What are we saying? Yeah, they're definitely going to be disjoint. These are not going to happen at the same time. And so hint, hint, these are probably a little bit easier to find than these. We are going to do a few examples of these, and we'll probably get to a few examples of those. But if we're talking about a sum 2, 3, or 5, it might be beneficial to have that sort of chart. And so we made a chart like this last time with a 4-sided die. Here is my 6-sided die, my sum of, so last time I think we went from 2 to 8, right? Now we're just kind of extending the same thing. Now we're going from 2 to 12 in our sums, if we're doing 6-sided die. So I want occurrence out of the total number. So if I'm going 6 by 6, 6 times 6 squares, I think there's 36 squares. Here's what a sum of 2 looks like. I believe here's my sums of 3s. And I think they said 2, 3, 4, or 5. And I think I mentioned it back when we did Venn diagrams. But we want the total occurrences of those things, or the probability, or the number of events, or the number of times the event can occur out of the total number of outcomes. That's what I was trying to say. Okay. I think I might have did this one not reduced, but I typically reduce them. Although occasionally, sometimes it's better not to reduce stuff.
So do we not reduce it for this question?
I would reduce it probably on this one. For most stuff, I would reduce it. And when I say it's better not to reduce it, usually that's in your work. In your solution, you should probably reduce it. Like when we do those probability distribution tables and we have to go back and add up fractions, like I want the same denominator in my fractions. I add stuff up. And we talked a bit about it, but if I circle these sets, right? If I circle the sets of 2s, 3s, 4s, and 5s, we said these are not overlapping. They are disjoint. So if I look at these sets, the set of 2, the set of 3, the set of 4, the set of 5, these things are not crossing each other. So that's another way to kind of see that they're disjoint. And so I have, I believe, 10 occurrences. Where are we at? One more person. Stephanie, are you around? Oh my goodness, this is lagging. What is happening? There we go. Okay. I believe it should give you 10 out of 36, right? We get 10 of those different things. And another thing, when you see that word or, it's kind of like we're adding sets together. So we added the set of 2, we added the set of 3, we added the set of 4. 10 out of 36, when you reduce it, it's 5 out of 18. Yeah, so a lot of times if you look at your fraction, I think I said it earlier, but if both top and bottom are divisible by 2, usually that's the first thing you can try. You can try dividing by 2, dividing by 3, go through your primes. But yeah, so this is disjoint. The sets are not overlapping. We just add the sets up. Same thing here. Now we're doing cards. So a little bit of a story. I went to public school, and anytime we took a tax, STAR test, I think is what they're calling it nowadays, whatever they want to call it, standardized testing. If you got done early, this is all you did was play cards. So I'm fairly familiar with cards. with that said, we are at a college and people come in from everywhere and have all sorts of different backgrounds. And you realize you kind of take these things for granted when you have to start teaching people that have no idea what a playing card is. But I've done it. And so I have this layout here. And so if you need some help with it, these are the suits. We get 4 different suits. This is clubs, spades, hearts, and diamonds. We get ace, 2, 3, 4, up to 10, and we start going to our face cards. Sometimes an ace is a 1, sometimes it gets treated as 11. Depends what game you're playing. But these are the basic breakdowns of the cards. We get a jack, we get a queen, we get a king in the face cards. What else? They're numerically numbered. I think that's about it as far as the structure of the cards goes. Drawing either a black ace or a red king on one draw from a regular deck of cards. So let me maybe highlight that a little bit. We want a black ace or a red king. Is that, oh yeah, that's what they said. So I believe they're talking about those two or those two. And we want to know, is this a overlapping or disjoint question, I believe. So is there going to be anything in common if I talk about black aces and red kings or red kings? Oh, there we all answered. I don't know what's going. Okay. And then now, excuse me. Now they want us to find probabilities. There are, someone asked how many cards there were. I was kind of a smart ass. But I said, hadn't you ever played 52 card pickup? There are 52 cards in a deck. And let me tell you, if someone tells you, do you want to play 52 card pickup? The correct answer to that is no. It's just, it's one of those things, it's a non-game. It's kind of like snipe hunting, right? It doesn't really exist. Do y'all know what I'm talking about? Where you take the cards, you're gonna go, we're gonna play 52 card pickup, and you just like, you spill them all over the floor, and you go, okay, now pick them up. So stupid. Okay, so how many times does this occur? I want to either get a black ace or a red king. So how many cards am I talking about if I talk about black ace? Sorry, yeah, that's what I said. Black ace or red king. And then out of that, how many total cards are there? There's also things we can do with the symmetry of these cards. Like if I want to draw a spade out of this deck, I'm going to have a 1 in 4 chance of doing that, right? I know there's 13 out of 52 gives me 1 in 4. The other thing is if like I want to draw nothing but 6s, maybe that's 4 out of 52. Another way to do that is 1 out of the 13 cards that are in any suit. So you can use symmetries sometimes that might help you a little bit when we're dealing with cards. But this, there we go, 1 in 13, that's it. You're basically talking about 4 cards out of 52, that's 1 in 13. Now, what are they asking? I think we're doing independent. Let me clear my annotations to clear them. Exit out of that stupid thing. Okay, so drawing either a 10 or a heart from a regular deck of cards. Make circles around it if you have to. We want a 10 or we want a heart. Do those things overlap or are they disjoint? Let me see. Let's do some blue. I'm gonna do blue. I believe these are my hearts. And I believe if I want to draw a set around it, I believe these are my 10s. And now that I did that, I hope it's like pretty obvious. Are these overlap or are they disjoint? Come on. Okay. They are overlapping. What is that overlap called? What's the name of that overlap? Oh, come on, picture. Okay. So this is an overlapping set. It is going to be a little bit different. We want to draw a 10 or a heart from a regular deck of cards. So let's talk a little bit about this. Maybe we want to draw a 10 or a heart. Annotations. So I want to draw 10s or hearts. And so if I'm thinking about how many 10s there are 4 10s. There are 13 hearts. And if you tell me 17 is the number of cards I want to pick from, you're going to be off. Why is that?
Because we need to subtract the overlapping one.
Yep, one overlap, right? There's one that's an overlap. And I think I said it. What is that overlap called? Maybe that's a stupid question. There's a very, very specific name. When I'm talking about 10s, I'm talking about hearts. My overlap for that thing is called the 10 of hearts. They can occur at the same time is what it's saying, right? So anytime you do things that are overlapping, you have to account for that overlap. And why are we subtracting the overlap? Well, if you think about it, when we add these 13 hearts and when we add the 4 10s together, we added this 10 of hearts in there twice. So anytime you add two different sets, you actually add their overlap twice in there. And so in order to get rid of that, you have to subtract the overlap. So I think I did, yeah, that's it. 52. That's probably pretty good talking about this one. Let me answer it right quick. I'll probably be the last one typing mine in, hopefully. So we get what, 16 out of 52. If I reduce that, I think I'm getting 4/13. So what y'all got? All right, and let me clear my annotations. I remember something happened last class. They told on themselves without realizing it. Drawing 4 spades in a row from a standard deck of cards when the drawn card is not returned to the deck each time. This is a sorted probability. So this says use any method to determine. So they're not asking you whether things are with and statements. What was it? Independent or dependent. And they're not asking you the or statement, whether it is overlapping or non-overlapping, right? Now they're just trying to like get you to use all this information you had. So we want to draw 4 spades. So I want a spade. And I want a spade, and I want a spade, and I want a spade. So this is an and statement, although it didn't really like maybe specifically state it. But I'm thinking spade, 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 spade. I do have this broken down on the next slide. So if I want to draw 1 spade, I guess I'll give you that much. Drawing 1 spade, we get 13 spades. out of 52. And they say something, woo, moves down just a little bit. Right there, that word gives you a hint. If we don't return it, that does something to it. How many am I doing? 13. That's it. And I know we're doing a lot of gambling today, a lot of games. But these sorts of things, these concepts, right? It doesn't necessarily have to be a game. You could be talking about any sort of thing, vital statistics here even, right? You could be talking about your life here. Lots of different things this could apply to. I think I mentioned that, like, Cardano was one of the guys that did a lot of this, the work and probabilities. And he was a big time gambler. Where are we at? We got one more person. Where's my computer just slow? There we go. Yeah, that's it. 11 out of 41, 65. And so I gave you a little bit of a hint. But how do we find this? So my first ace, I believe, is 13 out of 52. Each one is going to go down one after that. So this is that dependent sort of pattern thing happening. We got our first spade, second spade, third spade. 17, 160. I believe is what I get for the top. 6 million something. I divide those. I get 11 out of 41, 65 is what we got. Questions about this? This is how they find, like, anytime you're watching, you know, we're basically starting to find poker hands here, right? I think if you wanted to do a fifth one, if we did a fifth one, I think we would get actually a flush, right? That's what they are if it's all in the same suit. How do we get our fifth spade? I like to call him David Spade sometimes. And you might figure it out, but if we do 11 out of 4165, I didn't do the decimal approximation, but this is giving you, oh, come on, text, 0.00264. So we're talking about something that's like, you know, a 0.2% chance or something like that. This is going to be very, very rare that you're going to get 4 spades in a row. It'll be even more rare that you get 5 spades in a row, which is a flush, right? That's why it's kind of high up there. And so the quality of, like, your hand is determined on basically on the probability that you get it in poker and a lot of things, right? But yeah, that's where we're going at here. We're finding, like, basically the probabilities of different kind of poker hands and stuff like that. Drawing either a face card, jack, queen, king, or a club from a standard deck of cards. Okay, so I got I was thinking. So I would circle it, maybe. That might help you. Circle what you're talking about. So let's do that. Let's go. I want my face cards. I got 4 different suits. I got 3 in each suit. You might have figured out there's 12 of those guys there. The other thing is a club. That's this row right here. So I don't know if I broke this one down. I think I quit breaking them down at some point. It's like mm-hmm. 12 of them are face cards. There's 13 in a suit. And if you do this for an OR statement, we should be adding these. That'll get you most of the way there. Did anybody say 25 out of 52? I hope not. Because we got to do what? There's 3 that are overlapping, right? So don't forget your overlap. This was what the moral of the story was, right? There are club faces. We get 12 face cards. We get 13 clubs. We add these together. We still have to subtract 3 for the overlap. So in the previous one, there was 1 card overlapping. Here, there are 3 cards overlapping. Ooh, we all got it. That's good. Good business. Is this the one? I think this is the one. I'm glad y'all are actually doing the work. In the back of the book, they didn't put their division sign, and I swear, like my last class, I had like at least 5 students that would just like put 1126. I'm like, dude, that's not even a probability. You're just looking at the back of the book and copying whatever they have in there. Which is that's what you want to do? Go ahead and do it. Like, but it's. I'm not trying to be rude, but it's just the stupid approach to like take the class, man. Like, you're sitting here paying for a class and like you're doing things to appease me. Like, I don't know how to say this, but screw me. Like, you're going to see me so little in your life, right? Like, you're going to come into this class and you're going to leave this class and you're probably never going to see me again unless you want to. Majority of people that take this class probably won't. They might see me out on the street. I'll wave and smile, whatever. But don't learn this stuff for me. Don't do stuff just to appease me, man. Like, do this stuff for you so much. Purchasing 5 winning lottery tickets in a row when each ticket has a 1 in 8 chance of being a winner. So they don't say it, but we're doing 5 lottery tickets, 3, 4, 5. And so I think what we're doing is an and probability. So I think we're trying to think if these are dependent or independent, I'm hoping is the first question. So if this one has a 1 in 8 chance, oof, writing it with the pad. So horrible. But it's got a 1 in 8 chance of winning my first lottery ticket. What about my second lottery ticket? Does that change at all? Think about what? Okay. You have a 1 in 8 chance of being a winner. Does that mean you got a 7 in 8 chance of not being a winner? Probably. It is a lottery ticket. Oh man, my thing is lagging because I answered and I don't answer. Two and 4. This might be a good question. It's kind of leading into the next section even, right? If I go out and buy a lottery ticket and it's got a 1 in 8 chance of winning, I go scratch off my first ticket. It's got a 1 in 8 chance of winning. What's the probability that my second ticket will win? Does scratching this ticket affect this one? It shouldn't, right? If I scratch one lottery ticket, the next lottery ticket's still going to have a 1 in 8 chance of winning. So I think 1 in 8, 1 in 8, 1 in 8. All right.
Oh, wait, I'm kind of confused. So would we add them?
So when we're doing and probabilities, if we added them, this would get larger and it would be more probable. We want something that's going to make it get smaller.
We multiply it.
Yeah, it should be multiplication. And so I believe your numerator is just 1, right? And I believe bottom is 8 to the 5th. But let's just say we did this. Let's say we lost and we lost and we lost and we lost. And I come up to my 100th ticket. And I'm still on my 100th ticket. What is the probability on that single ticket that I will win or lose? Still 1 in 8. If you have independent trials, it is not going to change that probability. And that's kind of leading into the next section with the gambler's fallacy and stuff like that. Runs happen. Still, each individual trial is going to be 1 8. Where are we at? Who's this? Is that Ricardo? Did you answer? There you go.
Yeah, I kind of got confused.
Oh, it's fine. 8 times 8 times 8 times 8 times 8 5 times gives me 32,768. So I believe it should be 1 out of 32,768. What'd y'all tell me? 32,768. That's it. 1 32,768 32,768. 1/8 is the single trial. We're doing 1/8 times 1/8 times 1/8 times 1/8 times 1/8. 5 times. Four rainy days in a row when the forecast calls for a 40% chance of rain each day. And this I gave it in decimal. So they gave us our probability in a percentage. So if we get a 40% chance of rain, what is the chance that we will get rain, 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 rain? Is what they're saying. 4 times. Is that what they're saying? Yeah. And put a leading 0. I don't think I put the other ones. 0, 2, 5, 6. Put a leading 0 on there.
Would this be the decimal?
Yeah, and so the decimal when you're doing 40% is what, 0.4? And so if it's a 0.4% chance on the first day, what's the chance it's going to rain on the second day? Does it raining, whether it rained on the first day or not, does it affect the chance of the second day? Here it says each day it's 40%, right? And so that should indicate that it's not changing. So it doesn't matter what's happening on one day. Ooh, I keep clicking off of stuff today really bad. There we go. Clicking on things I don't want to click on and clicking off of things I don't. My mouse pad dexterity is a little bit off today. What'd y'all tell me? Did y'all give me a fraction? 16 out of 625 should be the fraction. But it's 0.4 times 0.4 times 0.4 times 0.4. I think you might have missed one of the 0.4s if you got 0.064 or yeah. Is that what happened? 0.4 times 0.4 times 0.4. Yeah, so you just missed the 4th day. I think you did 3 days. All right, and I think we got 2 more questions left. I think this is the second to the last, and then we get a last one that's got 3 parts, but it's pretty straightforward, hopefully. Randomly meeting either a woman or a Republican in a group that's composed of 30 Democratic men, 20 Republican men. 50 Democratic women and 60 Republican ones. So how many people total is that? That's 30 and 20 and 50 and 60. I believe there's 160 people total. So if it helps you to add them all up, we're getting 160 total. And now I want to come through here and I want to look at, let's just look at the words woman or Republican. So how many of those fit that description? Ooh. All right, so what am I circling? I got 30 Democratic men. Is that a woman or a Republican? I don't think so. And so I want to do what? I believe this 20 are Republican. These 50 are women. These 60 are both Republican and women. So I believe I'm getting 130 out of 160 when I add those things together. Is that what y'all got? 13/16 when we reduce it? Yeah, that's it. Questions about this? This is an or statement. This is one where they don't overlap, right? So you're either Republican or you're Democrat. They're either identifying as a man or a woman. They're not identifying as both. Flipping a coin. Oh man, this is one I meant to throw in a number. 3 times is what it should say. I didn't fix this, and I meant to fix it. I want to flip a coin 3 times and getting either all heads or you can get all tails. So if you really wanted to, I guess you could go list them all out. I don't really want to have to do that every single time. How many different combinations should there be if I list them out?
8.
There should be 8. And I start with what? All heads. I think I end with all tails. So how many is that? Out of how many? Put my little ellipses in there. We got one more problem after this. Free throw problem is what we're going to figure out. It's got 3 different parts or something like that, but it's all kind of the same question. Or pretty close. What is saying? Did y'all tell me 1/8? If you told me 1/8, you didn't add them together. There were two things that I circled out of a total of 8. 8 27ths. I don't know where you're getting the 27ths from.
Is it because I thought the outcomes, I don't know. I thought all of them would be.
You're doing 3 to the third outcomes or something, right? Something like that.
I did 2 over. Oh, I forgot what I did.
I think you did 2 to the third over 3 to the third for some reason. Maybe you're doing 2/3 each time.
Yeah, that's what I did.
2/3 times 2/3 times 2/3. It should be. If you do a half times a half times a half, you can get that for heads, 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 right? And so it's 1/8. You could do it that way, actually, right? And so my heads, heads, heads probability and my tails, tails, tails probability, I think this is another way to do it. So this might be worthwhile talking about, actually. Yeah, I love it when y'all get stuff wrong. It reminds me I got stuff. So heads, heads, heads is a 1/8. And a tails, tails, tails is a 1/8. And if I think about one or the other, I can add these two probabilities together. That one's going to be 1/8. That one's going to be 1/8. So overall, it should be 2/8, right? When I add these things together. Or it should give me a 1/4 probability. So adding here. Yeah, adding here. Two eighths reduces to 1/4. Okay. The other way I was talking about, I guess if you wanted to, you could list out all your possibilities, right? It's heads, heads. There are going to be 8 total possibilities here. And so I'm going to circle 2 things out of 8 possible different combinations. Or 2 out of 8 should give me the 1/4. When you use and is usually when you multiply, because when you're using and, you're being very specific. And so if I want 1 head, that's going to be more probable than getting a head and a head, two heads, right? Getting 1 head is easier than getting 2 heads. So when you think about and probabilities, things should be getting smaller, should be multiplying. When you think about or probabilities, we're combining things. So we should be adding probabilities. We should be adding events. We should be adding the probabilities. One-on-one free throws. A basketball player is fouled in a 1-on-1 situation, meaning she is awarded 2 free throws, only if she makes the first free throw. Her season average for free throws is 70% or 0.7. So usually when they use the decimals, I'm going to use decimals in mine. Using her season average as a relative frequency probability. Oh, excuse me. Ability. Find the probability she will miss her first free throw. I can't. I'm going to drink some water upside down or something. Okay, so she's got a 70% chance of making it. Yes. What is the probability she will not make it or that she will miss it? I think.
Do we put it percentage-wise or decimal?
As a decimal. So anytime you get probability should be the decimal format. And this, I think this is kind of coming from the last one, right? If there's a 70% chance that she's going to make it, what's the probability she's not going to make it? You're either going to make a basket or you're not going to make a basket, right? And so we know that these things should sum up to what?
To 1?
It's like they are lawn mowing like right now as they're going past it. They should sum up to 1. So it's, if you're gonna speak loud. I don't know what to say. I can barely hear. I think they're almost done. But yeah, it should add up to 1. So if there's a 70% chance she's going to make it, there's a 30% chance she will not make it. And so now I think we're doing multiple baskets. The probability that she will make her first free throw and miss her second. So I guess she has to make. Oh, I'm just going to do it with some text, Matt. Make it. And then a miss. What is my probability here? What is my probability here? How do I figure out when both of those things happen together? So the probability she will make a basket is what, 0.7? The last one we just figured out, the probability she will miss is what, 0.3? So how do I combine these two things to figure out what happens when she does both of those things? That worked. Which one? Okay, so I believe we're going to multiply those two things together. So we're getting 0.21. So I think that what that is telling me is there is a 21% chance. What are y'all telling me besides that? Did y'all add them or something? 21 out of 100. That's it. Yeah, that's it. Y'all got it. Where is it going to go? Last question. The probability she will make both free throws. So if I'm betting on this girl to make one free throw, am I going to bet for her to make it or against her? She's got 70%. I'm probably going to bet for her to make one free throw. Now we're going to talk about making two free throws. And so if each of them is, 70%, what's the chance she will make it twice? And I didn't do this for my other class, but I have a picture in my head, so I'm just going to go ahead and do it. Make, miss, I know I might have did this in the notes, something like this. You can do things like this, might help you. I don't know. Let me finish doing this. Actually, we don't need these if I'm going to do this. I don't need these. If she misses the second time, she's not going to get a second basket. This looks like the possibilities that we could all come through. She can make it and make it. She can make it and then miss. Or she could just straight off miss off the bat. And so if I think about these, it's 0.49. It's 0.7 times 0.7. What else are we saying, man? 0.49. If she's got a 70% chance of making 1.4. Oh, the leading zero. Y'all got it correct. The computer's just being really picky. So I think we figured out all these probabilities. So let's see if this works out. If she makes it and makes it, there is basically a 49% chance. So I'm probably going to bet against her making it twice, is what that's telling me. If she makes it and then misses, this is the 0.21% chance. And then if she just straight up misses it, I believe this gives me the 0.3 chance. And if we add all these together, guess what? Let me double check. Yes, it should add up to 1. One of these things is going to happen, right? If she does free throws, she's either going to miss it and she's done. She's going to make it, or make it and miss it. So if we add these up together, this should be every possible sort of thing that could happen. We should add up to 1. Are there any questions about anything we did? Because that is my final problem for you today. So going quick review, 7A, we did probabilities. 7B, we're combining probabilities with ands and ors. So if we have an and statement, we're being very specific. Multiply your probabilities together. If you want this to occur and this to occur, it's going to be those probabilities multiplied together. The thing you also have to account for is whether they are dependent or independent. If it's dependent, like without replacement, something like that, you have to subtract 1 from top and bottom. If it is an or statement, we add the events together, how many times they occur. If there's an overlap, we have to subtract the overlap. Any questions? I think that pretty much gives you a quick summary of what we did today.